Imagine staring up at a clear night sky, taking in its serene beauty, the gentle twinkle of distant stars, the soft glow of the Milky Way stretching overhead. It's a view that has inspired poets, dreamers, and explorers for centuries, a canvas of cosmic tranquility. But what if I told you that behind that breathtaking facade lies a universe teeming with unimaginable dangers? The same cosmos that gifts us with auroras and meteor showers also harbors forces so powerful, so utterly destructive, they could erase entire solar systems in the blink of an eye. Welcome to a journey beyond the familiar, into the heart of darkness that lurks among the stars. Today, we're counting down the 25 most dangerous objects in the universe, entities and phenomena so fearsome, they defy human comprehension. From black holes with gravitational pulls that trap light itself, to rogue planets drifting silently through the void, capable of unleashing chaos on anything in their path. Each of these cosmic marvels holds the power to reshape galaxies, end life as we know it, and challenge everything we thought we understood about reality. This isn't just a list, it's an exploration of the extremes where beauty and terror exist side by side in the grand tapestry of space. So settle in and open your mind to the extraordinary. Whether you're a seasoned space enthusiast or simply curious about the mysteries beyond our world, this video will take you on a gripping tour of the universe's deadliest wonders. By the end, you'll see the night sky not just as a thing of beauty, but as a dynamic, sometimes violent arena where the laws of physics play out on scales we can barely imagine. Ready to begin our countdown? Let's dive in. Kicking off our countdown at number 25 are the invisible predators of the cosmos, rogue black holes. Unlike the supermassive black holes that anchor the centers of galaxies, these are stellar mass monsters, each weighing several times more than our Sun, yet they travel alone through the immense darkness between stars. Their story begins in chaos. When two black holes merge, the tremendous energy released can kick the newly formed object out of its host galaxy at incredible speeds, sending it on an eternal journey through the void. With no light to emit and no permanent home, they become nearly impossible to track, drifting silently like phantom sharks in the ocean of space. The true terror of a rogue black hole isn't just its power, but its stealth. Imagine one right now on a direct course for our solar system. We wouldn't see it coming. There would be no warning sign, no bright accretion disk to signal its approach. The first indication something was wrong would be subtle, a slight, unexplainable wobble in the orbits of the outer planets as its immense gravity began to tug at them. By the time its influence reached the asteroid belt, it would be far too late. The delicate gravitational balance that has kept our planets in stable orbits for billions of years would be utterly shredded. One by one, planets would be pulled from their paths. Some might be flung out of the solar system entirely into the freezing abyss of interstellar space. Others would be drawn into a death spiral, torn apart by tidal forces before being swallowed whole, leaving behind not even a whisper of their existence. The entire architecture of our cosmic neighborhood would be dismantled, consumed by an unseen force. And after the destruction was complete, the rogue black hole would simply continue on its way, leaving nothing behind but empty space, a ghost that devours and then vanishes without a trace. But the danger doesn't only lurk in the form of invisible predators. Hurtling through the vast expanses between galaxies are projectiles of unimaginable speed and mass, cosmic cannonballs born from the most violent events in the universe. At number 24 on our countdown are hypervelocity stars. These aren't your average, gently burning suns. These are entire stellar systems catapulted across space, some reaching speeds exceeding 1.5 million miles per hour. Their incredible journeys begin at the very heart of chaos, the supermassive black hole at the center of a galaxy. When a binary star system, two stars orbiting each other, ventures too close to this gravitational monster, a cosmic game of celestial pinball ensues. The black hole's immense gravity can capture one star, pulling it into a fatal orbit while slingshotting its companion outward with a tremendous burst of energy, ejecting it from the galaxy entirely. In other cases, the sheer gravitational shockwave from a supernova explosion within a dense star cluster can launch a star on a one-way trip into the void. One of the most famous examples is the blue straggler star known as HE 0437-5439. This massive star, several times heavier than our Sun, was discovered blazing a trail out of our own Milky Way, moving so fast it has enough velocity to escape our galaxy's gravitational pull forever. It's a lone wanderer on an infinite journey through intergalactic space. Now, picture such a star on a collision course, not with a planet but with an entire solar system. The initial approach would be deceptively quiet. The first real sign of catastrophe wouldn't be the star itself, but its immense gravitational field preceding it, a herald of destruction warping the fabric of space around it. As it plowed through a system like ours, its gravity would act like a colossal plow, violently perturbing the orbits of every planet, moon, and asteroid it passed. The delicate dance of orbits that sustains life would be thrown into utter disarray. Planets could be pulled closer to their sun, triggering runaway greenhouse effects that boil away oceans or flung into the deep freeze of the outer system. The cascading gravitational chaos would send asteroids careening inward, pummeling any inner planets with a relentless barrage of impacts, a scenario eerily similar to the extinction event that wiped out the dinosaurs, but on a potentially far grander and more final scale. The hypervelocity star itself might not even need to make direct contact. Its gravitational wake alone would be enough to sterilize a system, leaving behind a scattered collection of dead worlds and debris before the star continues on its relentless, high-speed path, utterly unaware of the ruin left in its wake. But for all their terrifying speed and gravitational might, these stellar interlopers are not the most concentrated form of destructive power in the cosmos. That distinction belongs to the stellar corpses left behind by the most massive stars, and among them, one type stands out as a true apocalyptic engine. At number 3 on our countdown of the most dangerous objects in the universe is the Magnetar, a neutron star that has taken the concept of a magnetic field and weaponized it on a galactic scale. To understand a Magnetar, you first have to understand the violent death that creates it. When a star significantly more massive than our Sun exhausts its nuclear fuel, its core collapses under its own immense gravity. This triggers a supernova explosion of almost incomprehensible power, blasting the star's outer layers into space while crushing its core into an ultra-dense sphere of neutrons. For most neutron stars, that's the end of the story, a city-sized object so dense that a single sugar cube-sized piece of it would weigh as much as a mountain. But in a rare few cases, the physics of that collapse are just right to create something far more extreme. If the infant neutron star is spinning at several hundred times per second, its interior behaves like a dynamo, amplifying its magnetic field to intensities that defy belief. The numbers involved are so large they become almost meaningless. A magnetar's magnetic field is a quadrillion times more powerful than Earth's protective magnetic shield. To put that in perspective, a magnetar located halfway between Earth and the Moon would easily erase the magnetic strips on every credit card on the planet. But its true danger lies not in its static field, but in the catastrophic instabilities it creates. This unimaginable magnetic pressure puts the neutron star's solid crust under immense strain, causing it to fracture and shift in events known as starquakes. A starquake on a magnetar is nothing like an earthquake. It is a rupture in a crust of material 10 billion times stronger than steel, and the energy released is staggering. In a mere tenth of a second, a single starquake can unleash more energy than our Sun will emit across 100,000 years. This energy erupts in the form of a gamma-ray flare, a focused beam of the highest energy radiation in the universe. One such event from a magnetar named SGR 0526-66 located in the Large Magellanic Cloud was detected in 1979. For a fraction of a second, it flooded Earth's upper atmosphere with more radiation than a typical solar flare, despite originating from outside our galaxy. It was so powerful that it saturated the detectors of every spacecraft that observed it. Now, imagine if a magnetar much closer to us, say, within a few thousand light years, were to unleash such a flare and Earth was in its direct line of fire. There would be no visible warning, no bright light in the sky. The first sign would be a wave of high-energy radiation slamming into our planet. This gamma-ray barrage would immediately begin to tear apart the molecular bonds in our upper atmosphere, chemically transforming it. The ozone layer, our planet's essential shield against the sun's harmful ultraviolet rays, would be obliterated within weeks. With that protective blanket gone, lethal levels of UV radiation would reach the surface, triggering a mass extinction event that would devastate the base of the food chain. The sky would glow with eerie, unnatural auroras as the dying atmosphere lit up under the onslaught, a beautiful and terrifying sign of a biosphere being sterilized from halfway across the galaxy. A magnetar doesn't need to consume us or collide with us. It can simply flicker and from an immense distance end the world as we know it. And yet, even the cataclysmic power of a magnetar pales in comparison to a cosmic weapon that is actively aimed, a cannon of such immense proportions that its barrel is an entire galaxy. At number 4 on our countdown are blazars, perhaps the most unnerving objects in the universe because their most destructive feature is their direct line of sight to us. A blazar is not just a random cosmic event, it is a conscious-seeming threat, a singularity that has literally set its sights on Earth. To understand a blazar, we must first journey to the chaotic heart of a distant galaxy, where a supermassive black hole, billions of times the mass of our Sun, reigns supreme. As vast clouds of gas, dust, and even entire stars are pulled into its accretion disk, the incredible friction and magnetic forces heat this material to millions of degrees, causing it to glow brighter than all the stars in the galaxy combined. This is what astronomers call an active galactic nucleus, but for some of these monsters, the real violence is channeled outward. Along the black hole's spin axis, powerful magnetic fields can funnel some of the infalling matter and accelerate it to nearly the speed of light, creating a pair of opposing jets that blast out across intergalactic space for hundreds of thousands of light years. A blazar is simply one of these active galaxies where, by pure cosmic chance, one of these relativistic jets is pointed almost directly at Earth. This alignment transforms it from a spectacular celestial object into a potentially existential threat. From our vantage point, we are staring straight down the barrel of the most powerful particle accelerator in the universe. The jet is a focused beam of every form of high-energy radiation imaginable: gamma rays, X-rays, and a constant stream of high-energy protons and electrons, all screaming across the void directly toward our planet. The sheer energy contained in these jets is almost beyond calculation. A single blazar's jet can outshine its entire host galaxy, emitting more light in a few minutes than our Sun will over its entire 10 billion-year lifespan. Markarian 421, one of the closest and brightest blazars, is a prime example. Located about 400 million light-years away in the constellation Ursa Major, it is a relentless and variable source of the highest energy gamma rays we can detect. Its violent flickers and flares tell us the story of a chaotic and unstable environment, where the beam aimed at us is constantly shifting in intensity. The true danger lies in the potential for a truly colossal flare. If a blazar like Markarian 421 were to experience a super flare and Earth remained in its crosshairs, the consequences would be slow-moving but inescapable. The initial wave of gamma rays and cosmic rays would take centuries to reach us, traveling at the speed of light. There would be no way to see it coming until it was already upon us. This radiation wouldn't cause fiery explosions or instant destruction. Its effect would be far more insidious and thorough. The high-energy particles would smash into our upper atmosphere with the force of a planetary-scale nuclear reaction, ripping nitrogen and oxygen molecules apart and triggering a cascade of chemical reactions. The result would be the same as a Magnetars strike, but potentially on a larger and more sustained scale: the complete annihilation of our planet's ozone layer. Without this protective shield, the sun's ultraviolet radiation would pour onto the surface, causing severe sunburn in minutes, damaging the DNA of plants and phytoplankton, and collapsing the foundational layers of the global food web. The sky would fill with a permanent, smog-like haze of nitrogen dioxide, staining the heavens a sickly brown and leading to widespread acid rain. It would be an environmental apocalypse delivered by a silent, invisible beam from a black hole halfway across the universe, a reminder that the greatest dangers are not always those we can see barreling toward us, but those that have already been fired. Yet for all the distant, aimed terror of a blazar, there exists a stellar danger far closer to home, a cataclysm waiting to happen within our own galactic neighborhood. Securing the number 5 spot on our countdown are Wolf-Rayet Stars, the volatile, brilliant, and short-lived titans of the cosmos. These are not ordinary stars enjoying a long, stable life. They are stellar behemoths in their final, desperate act, furiously burning through the last of their nuclear fuel at a breathtaking pace. Born with masses over 20 times that of our Sun, they have already expelled their outer layers of hydrogen through impossibly powerful stellar winds, revealing their scorching hot helium-burning cores to the universe. This exposes a surface hotter than 90,000 degrees Fahrenheit, causing them to shine with a fierce blue-white intensity that is both beautiful and terrifying. The immediate danger of a Wolf-Rayet star is the unrelenting hurricane of radiation that defines its existence. These stars generate stellar winds so powerful they dwarf the solar wind our Sun produces. We're talking about a continuous supersonic blast of charged particles moving at over 5.5 million miles per hour, stripping away the star's own mass at a rate that would vaporize Earth in an instant. This ceaseless outflow creates a vast, expanding nebula of ejected material that glows under the intense ultraviolet radiation, effectively surrounding the star with a constantly growing bubble of its own scorched remains. Any planet or developing solar system within light years of such an object would be continuously sterilized, its atmosphere stripped away and its surface baked by this perpetual cosmic fallout. However, the true apocalyptic threat a Wolf-Rayet star possesses is reserved for its grand finale. These stars are primed to die in spectacular supernova explosions, but for some, there is a possibility of an even more extreme and rare death, a gamma-ray burst. For this to occur, the star must be rapidly rotating. As it collapses at the end of its life, this rapid spin focuses the incredible energy of the supernova into two narrow, opposing jets of pure gamma radiation that scream out along the star's rotational axis at nearly the speed of light. These jets contain more energy in a few seconds than our Sun will emit across its entire 10 billion-year lifespan, making them the most luminous electromagnetic events known in the universe. This brings us to WR-104, a Wolf-Rayet star located in our galaxy roughly 5,400 light-years from Earth in the constellation Sagittarius. Through telescopic observation, we've discovered something chilling. We are not looking at a simple star, but a binary system where the Wolf-Rayet star is actively cannibalizing its companion. More importantly, from our vantage point, we are looking almost directly down the barrel of its rotational axis. The system is tipped toward us, presenting a stunning pinwheel-shaped nebula created by the colliding winds of the two stars, a beautiful spiral that, tragically, also appears to mark the precise direction a potential gamma-ray burst jet would travel. The question, then, is not just if WR-104 will produce a gamma-ray burst, but what would happen to Earth if it did. If that jet were to hit our planet, the initial flash of gamma rays would last only a matter of seconds, but that would be more than enough. The radiation would violently deposit its energy into our upper atmosphere, instantly transforming vast quantities of nitrogen and oxygen into nitrogen dioxide, a thick, brown pollutant. The sky would literally change color, turning a murky, ugly brown as this smog-like haze began to block out sunlight. This would trigger a catastrophic chain reaction. The ozone layer would be devastated, surface temperatures would plummet from the resulting semi-permanent twilight, and acid rain would pour down for years. The simultaneous loss of sunlight and protection from ultraviolet rays would cripple photosynthesis, collapsing the entire planetary food web from the ground up. It would be an extinction event on a scale not seen for hundreds of millions of years, all initiated by a stellar explosion that occurred 5,400 years ago, the light from its destructive beam only reaching us now. The haunting reality is that WR-104 could have already gone supernova, and its final, deadly message could be traveling toward us at this very moment, a silent and invisible wave of annihilation already en route. While we have been looking at the dangers of stars and distant galactic cores, some of the most insidious threats are the ones we cannot see, moving silently through the dark. At number 6 on our countdown, we find the dark wanderers of the galaxy, the rogue planets. Picture a world like Jupiter, a colossal sphere of gas with dozens of moons in its sway. Now imagine the cataclysm that could tear such a giant from its home star and send it careening into the interstellar abyss, a frozen, sunless nomad on an eternal journey. This is not science fiction, it is a common and terrifying reality of our dynamic universe. The birth of a solar system is a violent and chaotic process, a gravitational tug-of-war between young, forming planets. In this fray, a close encounter between two gas giants can be catastrophic. One can be slingshotted with such force that it achieves escape velocity, breaking free from its star's gravitational pull entirely. Ejected from its cradle, it is condemned to wander the immense, cold space between stars, its atmosphere slowly freezing into a crust of ice over billions of years. These planets emit no light of their own and reflect almost none, becoming virtually invisible against the blackness of space. Current estimates suggest there could be billions, even trillions, of these dark giants adrift in our galaxy alone, a hidden population of gravitational landmines. The true peril of a rogue planet lies in its stealth and its sheer mass. A Jupiter-sized object possesses a gravitational influence that extends for billions of miles. Our solar system is not a tightly sealed fortress. It is surrounded by the vast, diffuse sphere of icy bodies known as the Oort cloud, which extends nearly a light year from the Sun. This is the first line of defense, and it is incredibly vulnerable. A rogue planet would not need to plunge directly into the inner solar system to wreak absolute havoc. Its approach would be silent and utterly undetectable with current technology until it was already deeply disturbing the outer reaches of our system. As it passed through the Oort cloud, its gravity would act like a colossal plow, shaking loose countless comets from their stable orbits and sending a storm of icy missiles raining inward toward the Sun and directly through the planetary zone where Earth resides. This would trigger a comet shower thousands of times more intense than any in recorded history, a continuous bombardment that could last for millions of years, making the asteroid impact that doomed the dinosaurs seem like a mere firecracker. But the direct gravitational effects would be even more catastrophic. The delicate balance of our solar system, a clockwork of orbits refined over 4.5 billion years, would be violently disrupted. The rogue planet's gravity could tug Uranus or Neptune from their paths, which would in turn perturb the orbits of Saturn and Jupiter. The cascading chaos could fling inner planets like Mercury, Venus, or Earth into wildly eccentric new orbits. We could be pulled closer to the sun, our oceans boiling away under a scorching sky, or hurled outward into a deep freeze, our world becoming an ice-balled rock. In the worst-case scenario, Earth could be ejected from the solar system entirely, becoming a rogue planet itself, a frozen tomb drifting forever in the interstellar night. And after unleashing this cosmic chaos, the rogue planet would simply continue on its way, a dark ghost that forever altered a star system without ever being seen. While rogue planets represent a slow-moving, gravitational threat, the universe also possesses triggers for destruction that are instantaneous and utterly relentless. Claiming the number 7 spot on our countdown are gamma-ray bursts, the single most powerful explosions known to exist since the Big Bang itself. These are not the comparatively gentle flickers of a Magnetar starquake or the sustained beam of a blazar. A gamma-ray burst is a sudden, catastrophic detonation of pure energy that can, for a few terrifying seconds, outshine every star in 100 billion galaxies combined. These cosmic blasts are categorized into 2 main types, but for sheer scale of annihilation, the long-duration gamma-ray bursts are the true monsters. Their origin story begins with the death of a very specific kind of star, a hypergiant, a behemoth dozens of times more massive than our Sun, with rapid rotation and low metallicity. When such a star exhausts its nuclear fuel, its core doesn't just collapse into a neutron star, it collapses directly into a black hole, as material from the outer layers rains down onto this newborn singularity. A portion of it is redirected by powerful magnetic fields and the star's own rapid spin. This material is funneled into 2 narrow, opposing jets that erupt from the star's poles at over 99.99% the speed of light. These jets are the gamma-ray burst, and they drill their way out of the dying star, punching through its surface to unleash their fury across the cosmos. The energy released in this event is so concentrated and so extreme that if one were to occur within our galaxy, the effects would be apocalyptic even from a significant distance. A gamma-ray burst within 6,000 light-years of Earth would deliver a direct, concentrated blast of high-energy radiation to our planet. The initial flash, lasting from a few seconds to several minutes, would deposit enough energy into our atmosphere to initiate a series of chemical reactions on a global scale. The gamma rays would break apart nitrogen and oxygen molecules, recombining them into nitrogen dioxide, a noxious brown gas. In a matter of days, our sky would literally turn a murky, soupy brown, blotting out the sun and casting the planet into a prolonged twilight gloom. This is where the true extinction-level sequence begins. The chemical changes would utterly obliterate the planet's protective ozone layer, leaving every living thing on the surface exposed to the full, unfiltered intensity of the sun's ultraviolet radiation. The loss of sunlight would crash global temperatures, triggering a rapid ice age. The combination of freezing cold, acid rain from the atmospheric pollution, and DNA-shredding UV light would be a cocktail that most complex life could not survive. The base of the food chain, phytoplankton and plants, would collapse, leading to a domino effect of starvation and extinction. This is not merely a theoretical scenario. Some paleontologists and astrophysicists point to a major extinction event that occurred around 445 million years ago, the Ordovician-Silurian extinction, as a potential candidate for a past gamma-ray burst strike. This event was peculiar. It resulted in the loss of an estimated 85% of all marine species, and the pattern of extinction suggests a sudden, catastrophic cause that particularly affected shallow water life, which would have been most vulnerable to a sudden blast of UV radiation. While the evidence is not conclusive, it remains a compelling and sobering hypothesis that one of the 5 great mass extinctions in Earth's history may have been triggered by a stellar explosion from a distant part of our galaxy. The probability of a nearby gamma-ray burst happening in the modern era is incredibly low. The type of stars that produce them are rare in our galactic neighborhood, and the jet must be pointed with precision directly at Earth for us to experience the full effect. Statistically, we are likely safe, but the profound implication remains: a single random stellar death occurring thousands of light years away has the potential to irrevocably alter the course of life on our planet without any warning. It is a reminder that we exist in a cosmos where the most violent events are not always dramatic collisions, but silent, invisible beams of energy that travel for millennia before delivering their fatal message. Yet for a brief, terrifying moment, one of these beams of pure energy was pointed directly at our planet. In 2008, the Swift satellite detected a gamma-ray burst so powerful that its afterglow was briefly visible to the naked eye from Earth, despite originating from a galaxy 7.5 billion light-years away. For nearly a full minute, this single event outshone every star in our own galaxy, a stark demonstration of the raw, universe-altering power that is constantly at play in the darkness. And while we are likely safe from such an event within our own galactic neighborhood, it serves as a humbling reminder of our fragile place in a cosmos capable of such instantaneous, staggering violence. But what if the danger wasn't a fleeting beam, but an entire cosmic engine of destruction, one that could rage for millions of years? At number 8 on our countdown, we encounter the ultimate active galactic nucleus, a phenomenon so luminous it can redefine the center of a galaxy, the quasar. The term itself, short for quasi-stellar radio source, hints at its initial mystery, appearing like a single, brilliant star in early telescopes, yet possessing a power that dwarfed entire star systems. We now understand a quasar to be the intensely bright beacon of a supermassive black hole in a state of insatiable gluttony, a vortex of matter and energy so potent it can influence the evolution of an entire galaxy. The engine of a quasar is a black hole with a mass ranging from millions to tens of billions of times that of our Sun, but it is not the darkness of the singularity itself that creates the brilliance. It is the frenzied chaos of its accretion disk, as vast clouds of gas, dust, and even entire stars are drawn inward by the black hole's irresistible gravity. They don't simply vanish. Instead, they spiral into a flattened, superheated disk rotating at nearly light speed. The friction and immense gravitational forces within this maelstrom heat the material to temperatures of millions of degrees, causing it to glow with a blinding light that can outshine the combined output of every single star in its host galaxy. This is the primary source of a quasar's staggering luminosity, a beacon visible across the universe. However, the true destructive power of a quasar is not just its light, but the colossal jets it can launch. Along the rotational axis of the black hole, powerful magnetic fields are wound up by the churning disk, acting like a cosmic railgun. These fields channel and accelerate a fraction of the infalling particles to relativistic speeds, blasting them out into space in two opposing beams that can extend for hundreds of thousands of light years. These jets are not mere streams of light. They are a focused torrent of high-energy radiation and elementary particles moving at over 99% the speed of light. Where these jets slam into the slower-moving intergalactic medium, they create massive lobes of radio emission visible across vast cosmic distances. The impact of a quasar on its host galaxy is catastrophic and transformative, a process known as quasar feedback. The intense radiation pouring from the central engine exerts an immense outward pressure, effectively blowing away the very gas clouds that are the raw material for new star formation. This strips the galaxy of its future, preventing the birth of new stars and essentially shutting down the galaxy's growth. In this way, a quasar acts as a cosmic regulator, its furious appetite ultimately leading to its own starvation and the transition of its galaxy into a quieter, red and dead elliptical state, populated by aging stars with no new generations to follow. The most powerful quasars can even influence structures far beyond their own galactic borders. Their jets can plow through the tenuous gas that exists between galaxies within a cluster, heating it and preventing it from cooling and collapsing to form new galaxies. This makes the quasar a dominant force on a truly intergalactic scale, an engine that can dictate the evolution of matter for millions of light years around it. We are witnessing the life cycle of galaxies themselves, where a period of brilliant, violent quasar activity is a pivotal phase that shapes their ultimate destiny, a testament to the fact that even the largest structures in the universe are not immune to the destructive power locked away in their hearts. Lurking in the vast dark between the stars are cosmic imposters, objects that blur the line between planet and star. Taking the number 9 spot on our countdown are brown dwarfs, the failed stars of the universe. These celestial bodies form just like true stars from the collapse of a gaseous cloud, but they simply never gathered enough mass to ignite sustained nuclear fusion in their cores. They are too massive to be considered planets, often weighing between 13 and 80 times the mass of Jupiter, yet too small and cool to truly shine. Instead of burning with the fierce light of hydrogen fusion, they merely glow with a dim, deep red heat, the fading remnant of their gravitational birth and the slow burn of a heavier element like deuterium. This dimness is the source of their danger. They are incredibly difficult to detect. A brown dwarf could be drifting through the outer reaches of our solar system right now, and we might not know it was there until its gravity had already begun to unravel the delicate balance of our cosmic neighborhood. But their threat isn't just one of stealthy approach. Some of these failed stars may not be traveling alone. Theoretical models suggest that brown dwarfs, much like Jupiter, could have formed within their own miniature solar systems, complete with a family of orbiting exomoons. These moons, warmed by the faint infrared glow and tidal forces of their dark host, could potentially maintain liquid water oceans beneath icy shells, creating hidden, solitary pockets of habitability adrift in the eternal night. This possibility transforms a brown dwarf from a simple gravitational hazard into a potential carrier of alien ecosystems, a wandering world with its own hidden biosphere. But for our solar system, the more immediate concern remains their immense gravitational influence. The true nightmare scenario begins when one of these dark, massive objects makes a close pass through the Oort cloud, the vast spherical shell of icy planetesimals that surrounds our solar system far beyond the orbit of Neptune. This cloud is the source of long-period comets, and its objects exist in a fragile, frozen equilibrium. The gravity of a passing brown dwarf, hundreds of times more massive than Jupiter, would be like throwing a boulder into a still pond. It would create a profound gravitational disturbance, shaking loose countless icy bodies from their stable orbits. This would trigger a cascade of chaos, sending a hail of comets screaming inward on new, deadly trajectories straight through the heart of our planetary system. The inner solar system would experience a cometary bombardment of unprecedented scale, an event that would make the late heavy bombardment in our solar system's early history look like a light shower. Earth would find itself in the crosshairs of this celestial shooting gallery, facing a dramatically increased risk of a catastrophic impact from a comet several kilometers wide, an impact with the power to plunge the planet into a years-long impact winter and cause a mass extinction. The most chilling aspect of this threat is its timescale. The disturbance wouldn't be a single, sudden event. The cometary shower could last for millions of years, a prolonged period of elevated danger that would fundamentally alter the climate and evolutionary trajectory of our planet. And after unleashing this torrent of icy missiles, the brown dwarf itself would simply continue on its silent, dark path through the galaxy, utterly unaware of the lasting chaos it left in its wake, a grim reminder that some of the universe's most dangerous objects are those we can barely see. But the universe holds even more exotic and hostile real estate, worlds that make a brown dwarf's dark moons seem almost hospitable. At number 10 on our countdown, we enter the terrifying domain of pulsar planets, worlds that orbit the most precise and deadly timekeepers in the cosmos. To find them, we must return to the aftermath of a supernova where a neutron star is all that remains. But this is no ordinary neutron star. It is a pulsar, a stellar corpse spinning hundreds of times per second, beaming out intense radiation from its magnetic poles like a relentless cosmic lighthouse. These beams are not gentle rays of light. They are focused cones of lethal radiation, X-rays and gamma rays sweeping through space with metronomic precision. The discovery of planets orbiting such an object was a profound shock to astronomers. The very idea seemed impossible. How could a world form from the chaotic debris of a star that had just torn itself apart in a cataclysmic explosion? The leading theory suggests that these are second-generation planets, not survivors of the blast, but worlds born from the ashes. The supernova's fury likely stripped any original planets away, but the ejected material falling back onto the pulsar could have formed a new, dense disk of matter from which a fresh set of planets coalesced. To exist in such a system is to live in a perpetual state of siege. Any planet orbiting a pulsar is subjected to a constant, bathing horror of high-energy radiation. Its surface would be instantly sterilized, its atmosphere, if it ever had one, scoured away by the relentless particle wind. These are barren, blasted rocks, their surfaces likely fused into a strange, glassy crust by the endless radiation bombardment. The pulsar's incredible gravity would also lock these planets into tight, incredibly fast orbits. A year on such a world might last only a few Earth days, a frantic rush around a ticking radioactive heart. The most famous example, PSRB 1257+12, discovered in 1992, hosts a system of at least 3 such planets. This pulsar, located about 2,300 light-years away, spins over 160 times per second, meaning its deadly beams sweep across its planetary children with a frequency that is both mind-boggling and terrifying. These worlds are quite literally being microwaved and X-rayed into oblivion, a testament to life's inability to gain a foothold in the universe's most extreme environments. Now let's bring this nightmare closer to home. Imagine if such a pulsar, ejected from its own system and gone rogue, would make a close pass through our solar system. Its approach would be silent, its visible light negligible. The first sign of its arrival would not be visual, but a storm of interference across our radio telescopes and a sudden, alarming spike in radiation readings from satellites. As it drew nearer, its precise, lighthouse-like beams would begin to sweep across the planets of our solar system. Wherever those beams touched, devastation would follow. If one were to sweep across Mars, it would strip what little atmosphere remains. If it crossed Jupiter, it would violently ionize the gas giant's upper cloud decks, creating spectacular but deadly auroras on a global scale. But the true terror would be if Earth found itself in the crosshairs. The beam's passage might only last for a few minutes or hours, but that would be more than enough. It would act like a cosmic blowtorch, delivering a dose of radiation equivalent to millions of chest X-rays per second to the upper atmosphere. This would instantly create massive amounts of nitrous oxides, shredding our ozone layer in a single, swift pass. The sky would temporarily glow with an eerie, unnatural light. The immediate radiation surge would cripple satellites and pose a severe radiation risk to any astronauts in orbit or even passengers on high-altitude flights. While it might not cause an instant extinction, the long-term damage to our planet's protective blanket would be severe, leaving us vulnerable to increased solar ultraviolet radiation for decades to come. The pulsar would then continue on its way, its rhythmic ticking fading from our detectors, leaving behind a solar system subtly but permanently scarred by the passing of a dead star's touch. But as we contemplate the external threats from pulsars and rogue planets, an even more unsettling danger might be lurking within the very fabric of space itself, a form of matter so mysterious it makes the vacuum of space seem solid by comparison. At number 11 on our countdown, we confront a hypothetical but deeply terrifying possibility: dense clouds of dark matter, For decades, we've understood that this invisible substance makes up the vast majority of the matter in the universe, a cosmic scaffolding that holds galaxies together with its gravity. But what if this dark matter isn't always smoothly distributed? What if it could clump together into dense, planet-sized masses that drift unseen through the galaxy? The standard model of cosmology suggests that dark matter forms an immense, diffuse halo around galaxies like our Milky Way. But some more exotic theories propose that certain types of dark matter particles, known as macroscopic dark matter or macros, could potentially aggregate into concentrated blobs with masses comparable to an asteroid or even a planet. These wouldn't be clouds of gas, they would be incredibly massive yet nearly transparent objects, their gravitational pull their only real signature. They would move silently through the interstellar medium, their presence virtually undetectable with our current technology until the moment they began to interact with a star system. The true horror of such an object is not a collision in the traditional sense, but a merger. A dense clump of dark matter would not be stopped by a planet's atmosphere or crust. Based on our current understanding, it would barely interact with normal matter at all. It would pass through the Earth as if our planet were a ghost, but its immense gravity would not be so easily ignored. As this invisible mass moved through our world, its gravitational field would rip through the planet's interior like a subterranean earthquake of unimaginable proportions. The solid rock of the mantle and core would be wrenched and distorted, not from the outside but from within. The geological catastrophe would be instant and global. Tidal forces from the passing mass would trigger volcanic super-eruptions at every major fault line, spewing enough ash and sulfur into the atmosphere to blot out the sun for years. The planet's crust would buckle and shear, generating magnitude 12 or higher earthquakes that would literally reshape continents in a matter of hours. The oceans would be thrown into chaos, with tsunamis thousands of feet high crisscrossing the globe and scouring coastlines clean of all life. The very magnetic field that protects us from solar radiation could be disrupted by the violent disturbance to our planet's liquid iron core, potentially weakening or even collapsing our protective shield for centuries. Perhaps the most chilling aspect of this scenario is its subtlety. From space, the event might look strangely peaceful. There would be no fiery impact, no brilliant flash in the sky. An observer might only see the Earth suddenly and violently convulsing, its surface transforming under a shroud of volcanic ash and steam, all triggered by an invisible, unknowable force that had already passed through and continued on its way. This is a danger that bypasses all our conventional defenses, a reminder that the greatest threats may not come from what we can see in the void, but from the invisible dark that fills it. Yet from the theoretical horror of dark matter to the silent menace of pulsars, we now turn to a cataclysm that is both a creator and a destroyer, an event of such profound duality that it forges the very elements of life while simultaneously unleashing forces capable of erasing it. Securing the number 12 spot on our countdown is the kilonova, the universe's ultimate alchemical furnace and one of its most violent spectacles. This is not the death of a single star, but the spectacular merger of two stellar corpses, neutron stars, in a cosmic collision that literally shakes the fabric of space-time and seeds the cosmos with the building blocks of planets and life, all while bathing everything in its vicinity in a wave of apocalyptic radiation. The stage for a kilonova is set over billions of years. It begins with a binary system of two massive stars, each destined to end its life in a supernova. If the stars are close enough, these explosions can leave behind a pair of neutron stars locked in a gravitational embrace, their orbits slowly decaying as they radiate energy away in the form of gravitational waves. For eons, these ultra-dense spheres spiral closer and closer, their dance accelerating until in a final, frantic millisecond they collide. The force of this impact is beyond comprehension. Two objects, each more massive than our Sun but compressed into a city-sized sphere, smash together at a significant fraction of the speed of light. The resulting explosion is a kilonova, briefly shining with the brightness of 100 million suns. The immediate aftermath of this merger is a maelstrom of creation and destruction. The incredible temperatures and pressures, combined with a torrent of neutrons, trigger a rapid process of nucleosynthesis known as the R process. In mere seconds, atomic nuclei are bombarded with neutrons, building them up into the heaviest elements in the periodic table. It is in these events that the universe forges vast quantities of gold, platinum, uranium, and other precious and radioactive elements. A single kilonova can produce more gold than the entire mass of our Earth, scattering these newly minted atoms out into the surrounding cosmos at incredible speeds, where they will eventually be incorporated into new generations of stars and planets. The very gold in your jewelry was likely born in such a cataclysmic explosion billions of years ago. However, for any hypothetical planetary system within a few dozen light years of this event, this act of creation would be a prelude to doom. The merger unleashes two primary lethal phenomena. The first is a short gamma-ray burst, an intense flash of the highest energy radiation that, although lasting less than 2 seconds, is more energetic than our Sun, will be across its entire 10 billion-year lifespan. This beam of gamma rays, if pointed directly at a world, would deliver a crippling blow to its atmosphere, ionizing gases and shredding the ozone layer in an instant, leaving the surface exposed to deadly ultraviolet radiation from its own star. But the gamma-ray burst is merely the opening salvo. The real and prolonged threat comes from the radioactive debris ejected during the explosion. The kilonova hurls out a superheated cloud of this material, laced with newly synthesized heavy elements like iodine, cesium, and uranium, all intensely radioactive. This expanding shell of death would wash over a nearby planetary system days or weeks after the initial flash. The effect would be a continuous rain of radiation from the sky that could last for years. The surface of any planet would become uninhabitable, bathed in a constant lethal dose of radiation that would cause widespread mutations, cancers, and the collapse of complex ecosystems. It would be a slow, silent extinction, with the very elements necessary for advanced life also acting as the agents of its demise. The evidence for this dual nature of kilonovae moved from theory to stunning observation in 2017 with the event known as GW170817. For the first time, astronomers detected the gravitational waves from the merging neutron stars with LIGO and Virgo, and then pinpointed the location to watch the entire event unfold across the electromagnetic spectrum, from gamma rays to radio waves. They witnessed the creation of heavy elements in real time, confirming that these fantastic explosions are indeed the cosmic forges for gold and other rare elements. This single observation, watching a kilonova birth the stuff of treasure and terror simultaneously, forever cemented our understanding of these events as some of the most powerful and paradoxical in the cosmos. But now we arrive at a stellar bomb so precise, so uniform in its destructive power, that astronomers use it as a cosmic measuring stick to chart the expansion of the universe itself. At number 13 on our countdown, we find the Type Ia supernova, the thermonuclear inferno of a white dwarf star. This isn't the chaotic collapse of a massive star. It is a detonation of such perfect and predictable violence that it can outshine an entire galaxy, yet its very uniformity makes it one of the most reliable and terrifying cosmic phenomena. The fuse for this explosion is lit in a binary star system, where a white dwarf, the incredibly dense Earth-sized core of a sun-like star that has exhausted its fuel, orbits a companion. This white dwarf is a degenerate sphere of carbon and oxygen, supported not by nuclear fusion but by the sheer quantum pressure of its electrons. It is a stellar ember slowly cooling over billions of years. But if this white dwarf has a close stellar partner, its peaceful retirement can be violently interrupted. It can begin to gravitationally siphon material, primarily hydrogen, from its companion star. This stolen matter accumulates on the white dwarf's surface, building up layer by layer, increasing the pressure and temperature at its core. As the white dwarf's mass approaches the Chandrasekhar limit, a critical threshold of about 1.4 times the mass of our Sun, the conditions in its core become hellish. The immense pressure ignites carbon fusion everywhere throughout the star's interior simultaneously. This is not a gentle burn, it is a runaway thermonuclear chain reaction. In less than a second, the entire white dwarf is engulfed in a flame front moving at a significant fraction of the speed of light. The star is not just exploding, it is being completely obliterated in a titanic release of energy, forging a fireball of incandescent iron and radioactive nickel. For a few weeks, this single object can emit more light than every one of the hundreds of billions of stars in its host galaxy combined. The elemental fallout from this cataclysm is its creative legacy. The incredible energies involved fuse a colossal amount of iron, roughly the mass of our entire planet, forged in an instant, with enough iron produced to make over 600 million Earths. This iron, along with other heavy elements, is blasted out into the interstellar medium at speeds of thousands of miles per second, eventually seeding future generations of stars and planets. The very iron in your blood, the steel in our cities, was once forged in such a stellar explosion billions of years ago. However, for any world unfortunate enough to be living in the galactic neighborhood of such an event, this act of creation is indistinguishable from pure annihilation. A Type Ia supernova is a threat on two fronts: the initial flash of radiation and the ensuing shockwave of expanding debris. If one were to occur within about 50 light-years of Earth, the effects would be devastating. The first sign would be a new star appearing in the sky, rapidly brightening until it rivaled the full moon, visible even in broad daylight, but this is no harmless light. This brilliant point is emitting a torrent of high-energy radiation, including a massive surge of X-rays and ultraviolet light. This radiation would strike our atmosphere like a physical blow, ionizing gases and initiating a complex series of chemical reactions. The most catastrophic result would be the rapid depletion of the ozone layer. Within days, our planet's protective shield against the sun's harmful UV radiation would be severely compromised, leaving every living thing on the surface exposed to a lethal dose. The aftermath would be a biological catastrophe. Phytoplankton in the oceans, the foundation of the marine food web, would be decimated. Land plants would suffer severe genetic damage and stunted growth. Animals, including humans, would face widespread cancers and cataracts. The collapse of the base of the food chain would trigger a global famine and a mass extinction event. And this is just from the light of the explosion. Centuries later, the physical shockwave of expanding debris would finally arrive, a wave of radioactive gas and dust that would further bombard the solar system, potentially enhancing the greenhouse effect and prolonging the environmental disaster for millennia. The sobering reality is that we know of several white dwarf systems within this danger zone. One of the most prominent is Ik Pegasi b, a massive white dwarf locked in a close orbit with a companion star, located only 150 light-years away. While it is not currently accreting mass at a rate that would make it an immediate threat, its existence serves as a stark reminder that such stellar bombs are not just theoretical dangers in far-off galaxies. They are a present and potential future hazard in our own cosmic backyard, a silent countdown held in the gravitational embrace of binary stars. Venturing now from the isolated stellar explosions and wandering dark matter, we arrive at the most immense and enduring source of danger in our entire galaxy, an ancient gravitational monarch lurking at the very crossroads of the Milky Way. Claiming the number 14 spot on our countdown is the supermassive black hole at the galactic center, our own Sagittarius, a star. This is not a mere stellar remnant, it is a cosmic titan, weighing in at a staggering 4 million times the mass of our Sun. A silent predator sitting at the heart of the intricate stellar dance that defines our island universe. For most of the time, Sagittarius A star is a relatively quiet beast, existing in a state astronomers call quiescence. It is not actively consuming large amounts of matter, and its emissions are relatively low. But this quietude is deceptive, a mere pause in a cycle of violence that has shaped the entire galaxy. The environment around it is anything but peaceful. The galactic center is the most densely packed region of stars in the entire Milky Way, a stellar metropolis where millions of suns are crammed into a relatively small volume of space. Here, stars whip around the central black hole at breathtaking speeds, some completing an orbit in just a few Earth years. This chaotic, high-speed traffic creates an environment of perpetual peril, where close encounters and violent collisions are not just possible but inevitable. The true danger of this region manifests during the black hole's occasional feeding frenzies. When a stray gas cloud, like the infamous G2 cloud, or an unfortunate star ventures too close, it is captured by the black hole's irresistible gravity. The object is not simply swallowed whole, it is torn apart in a spectacularly violent process known as spaghettification. The tidal forces from the black hole, the difference in gravitational pull between one side of the object and the other, overwhelm the object's own gravity, stretching it into a long, thin stream of superheated plasma. This material then spirals into the accretion disk, a maelstrom of friction-heated gas that can reach temperatures of millions of degrees. As this matter plummets toward its doom, it releases a torrent of high-energy radiation across the entire spectrum, from X-rays to gamma rays, transforming the galactic center into the universe's most powerful flashbulb. For any hypothetical world that might somehow form in this chaotic region, the conditions would be utterly incompatible with life as we know it. The first and most constant threat would be the relentless bath of ionizing radiation. The sheer density of stars means the night sky would never truly be dark, perpetually illuminated by the glow of nearby suns and constantly peppered with the lethal radiation from stellar winds and supernova occurring with frightening frequency. But the occasional outburst from Sagittarius A star itself would be the true extinction-level event. A major X-ray or gamma-ray flare from an accretion event would deliver a lethal dose of radiation to any planet within hundreds of light years, instantly sterilizing its surface and stripping away any atmosphere it might have possessed. The very forces that stir the pot of galactic evolution, creating the heavy elements necessary for planets and life, also ensure that the galactic downtown is a permanent dead zone, a radiant hellscape where complexity is born only to be immediately shredded by forces beyond comprehension. It is the ultimate cosmic paradox, a creative heart that is also a place of absolute destruction. But our journey through the cosmos now takes us to a scale so vast it challenges comprehension itself. At number 15, we encounter a danger not of a single star or a black hole, but of an entire island of stars set on a destructive path, the runaway galaxy. Picture not just a star, but hundreds of billions of them, along with their planets, nebulae, and black holes, all moving as one coherent unit through the void at a significant fraction of the speed of light. This is the ultimate expression of cosmic violence, where the gravitational machinations of the universe can fling entire galaxies out of their clusters and set them on a collision course with destiny. The genesis of such a colossal event is a gravitational showdown of almost unimaginable power. It typically occurs within a dense cluster of galaxies, where these immense structures swing past each other in a slow billion-year dance. When two or three large galaxies pass extremely close together, they can engage in a gravitational slingshot maneuver. The smallest galaxy, caught in the gravitational pull of the larger ones, can be accelerated to incredible speeds and ejected from the cluster entirely, becoming a runaway, destined to travel the intergalactic voids alone. In other, even more violent scenarios, the immense gravitational energy released from the merger of two supermassive black holes at the center of a galaxy can provide a kick powerful enough to send the entire galaxy recoiling outward. One of the most stunning real-world examples of this phenomenon is the Condor Galaxy, formerly known as NGC 4874. Observations show this spiral galaxy moving through space at a blistering pace, and it's trailed by a vast, complex stream of stars, gas, and dust that stretches for over 300,000 light-years. This magnificent tail is the evidence of its violent escape, material ripped away by the gravitational forces that expelled it from the Coma cluster. It is a celestial comet on a galactic scale, a runaway giant bleeding stars as it flees the scene of its cosmic birth. The danger posed by such a galaxy is not one of a direct, head-on collision with our Milky Way. The distances are far too vast for that. The true threat is to the stability of the local cosmic web and to any smaller, innocent galaxies that might lie in its path. A runaway galaxy like the Condor is a gravitational bulldozer. Its immense dark matter halo, which extends far beyond its visible disk of stars, would act as a massive plow blade. As it tears through a region of space, its gravity would perturb the orbits of every galaxy group and cluster it passes, potentially hurling smaller galaxies out of their own stable orbits and into the void or sending them on new, catastrophic collision courses with one another. For any dwarf galaxy unfortunate enough to be a direct companion or in its way, the encounter would be utterly devastating. The runaway galaxy's tidal forces, the difference in its gravitational pull from one side of the dwarf galaxy to the other, would be overwhelming. These forces would stretch and distort the smaller galaxy, pulling it apart in a process called tidal disruption. Streamers of stars and gas would be drawn out into long, luminous arcs, slowly feeding the larger galaxy while simultaneously tearing the dwarf apart. Over hundreds of millions of years, the dwarf galaxy would be completely cannibalized, its stars assimilated into the halo of the runaway giant or scattered into the intergalactic medium as a faint, mournful trail of cosmic debris. This is galactic ecology at its most brutal, where the largest predators consume the smallest, not with teeth and claws, but with the inexorable, invisible force of gravity. The runaway galaxy continues its journey, its path marked by the ruins of those it has destroyed, a sovereign state of stars imposing its chaotic will on the cosmos. Yet even the galactic-scale fury of a runaway giant seems almost orderly compared to the ultimate stellar death scream, a cataclysm so violent it represents a star tearing itself apart from the inside out. At number 16, we encounter the hypernova, the supernova's bigger, far more terrifying sibling. While a typical supernova marks the death of a massive star, a hypernova is the final, apocalyptic detonation of a true cosmic titan, a hypergiant star born with over 100 times the mass of our Sun. This isn't just an explosion, it's the universe's most powerful and destructive stellar-scale event, a death throw so energetic it can outshine entire galaxies and serves as the birth cry of the most dangerous objects we've yet encountered. The story of a hypernova begins with a star of almost impossible proportions. These are not the red supergiants we commonly picture. They are superluminous blue variables, incredibly massive, hot, and unstable behemoths that burn through their nuclear fuel at a ferocious rate, living fast and dying young in a blaze of glory. Their immense gravity creates core temperatures and pressures far beyond those in smaller stars, allowing them to fuse elements all the way to iron at a staggering pace. But iron is the ash of nuclear fusion. It cannot produce energy, and its accumulation in the core is a death sentence. In a star of this size, the iron core grows immense, and when it finally reaches a critical mass, its collapse is not just a failure, it is an utter catastrophe. The core's collapse does not halt upon forming a neutron star. The sheer mass raining down is too great, and the newborn neutron star is immediately crushed further under the weight, collapsing directly into a black hole. This is the pivotal moment that separates a supernova from a hypernova. The formation of this stellar mass black hole at the core is like pulling the cosmic plug on the entire star. The outer layers, with nothing left to support them, come crashing down at nearly the speed of light. However, not all of this material falls in. The newborn black hole's intense rotation and powerful magnetic fields act like an immense cosmic engine, channeling a fraction of the infalling matter into two ultra-relativistic jets that blast outward along the star's rotational poles. These jets, moving at over 99.99% of the speed of light, drill their way through the star's outer layers and erupt into the surrounding space, carrying with them an almost unimaginable amount of energy in the form of a long-duration gamma-ray burst. The energy numbers are simply baffling. A hypernova can release over 10 times more energy than a typical core collapse supernova. In a matter of seconds, its gamma-ray burst component can emit more energy than our Sun will across its entire 10 billion-year lifespan. For a brief moment, this single event becomes the brightest thing in the observable universe, outshining every star, quasar, and galaxy in its vicinity. The afterglow from the explosion itself can be seen for weeks, a fading beacon of a star's ultimate sacrifice. The most famous and well-studied example of a hypernova was the event known as SN 1998 BW. Its associated gamma-ray burst, GRB 980425, was a watershed moment in astronomy. For the first time, astronomers definitively linked a gamma-ray burst to a supernova explosion, but the light curve was far too bright and the energies far too high for a normal supernova. It was the smoking gun for the hypernova model, proof that the most extreme stellar deaths were responsible for the universe's most powerful explosions. The event was located in a galaxy about 140 million light-years away, a safe distance, but its detection served as a stark warning of the power lurking in the cosmos. Now imagine the consequences if such an event occurred within our own galactic neighborhood, say within 6,000 light-years of Earth. The focused jet of gamma rays, if pointed directly at us, would be only the first, most immediate threat. That initial flash would deliver a lethal dose of radiation to our upper atmosphere, but the prolonged aftermath of the hypernova itself would be just as devastating. The explosion would flood the surrounding interstellar medium with high-energy cosmic rays and intense ultraviolet radiation for centuries. Our solar system would be bathed in this persistent, deadly glow, further eroding our planet's protective layers and bombarding the surface with mutagenic particles. The hypernova is the ultimate cosmic death announcement, a final, brilliant testament to a star so massive that its very existence was a precarious balancing act against gravity. Its death creates the black holes that dominate our list of dangers and seeds the galaxy with the heaviest elements, but it does so at a cost that would be utterly apocalyptic for any nearby world. It is the pinnacle of stellar violence, a reminder that the universe operates on a scale of power where even the death of a single star can echo across the cosmos for millennia. Yet even the hypernova's focused beam of destruction is preceded by a far subtler signal, a ripple in the very fabric of space-time that announces the coming cataclysm. This brings us back to number 17 on our list, but to a far richer understanding of the kilonova. We've already seen it as a creator of elements and a source of radioactive fallout, but its true danger is announced by a whisper from the void, a gravitational wave. The detection of these waves has transformed this cosmic event from a theoretical model into an observed, terrifyingly precise process. The story begins not with light, but with a vibration. In the final moments before two neutron stars collide, locked in a death spiral that has lasted for millennia, their incredible masses whipping around each other hundreds of times per second create a wobble in the fabric of the universe itself. These gravitational waves, predicted by Einstein a century ago, radiate outward at the speed of light, stretching and compressing space itself by an almost imperceptible amount. For most of human history, this signal would have passed through our planet completely unnoticed, but on August 17, 2017, that changed forever. The twin detectors of the Laser Interferometer Gravitational Wave Observatory, LIGO, along with the Virgo detector, picked up a distinctive chirp, a rising frequency that signaled the final seconds of a binary neutron star system's life. This signal, named GW170817, originated from a galaxy 130 million light-years away in the constellation Hydra. This gravitational wave signal was the starting pistol for one of the most frantic and significant campaigns in modern astronomy. Within seconds of the detection, automated alerts were sent to observatories all over the world and in space. Telescopes of every kind swiveled to look at the patch of sky the signal came from. They were not searching for a bright explosion at first, but for a new, faint point of light, the kilonova. And they found it. What followed was a breathtaking multi-wavelength observation of the entire event, from the initial gamma ray burst to the unfolding thermal glow of the expanding debris cloud. For the first time, we had front-row seats to the complete life cycle of a cosmic catastrophe. The violence of the merger itself is where the dual nature of this event becomes so stark. As the two ultra-dense cores smash together, a fraction of their material isn't immediately swallowed by the newborn black hole. Instead, it's splashed outward and heated to extraordinary temperatures, forming a dense, hot cloud of neutron-rich debris. It is within this expanding cloud that the universe's most valuable alchemy takes place. Atomic nuclei are bombarded by a torrent of free neutrons in a process called rapid neutron capture, or the R process. This is how elements heavier than iron are forged: gold, platinum, neodymium, and radioactive elements like uranium and plutonium. The observed spectra of the kilonova's light confirmed it. This event was producing stupendous amounts of these heavy elements. The calculations are staggering. The merger likely produced an amount of gold with a mass several times that of our entire planet, along with other elements, all blasted out into space at a significant fraction of the speed of light. This is the beautiful part, the cosmic forge that creates the very elements that make up our jewelry and our technology. But this beautiful creation is inextricably linked to an incredibly violent and radioactive aftermath. The ejected material is not stable. It is a blazing hot soup of newly minted atoms, many of which are intensely radioactive. They decay rapidly, and the energy released from this decay is what powers the kilonova's visible glow, causing it to shine with a characteristic red color for several days before fading. For any world within, say, 50 light-years of this event, this expanding shell of precious metals would be a wave of death. It would arrive weeks after the initial gamma-ray flash, raining down upon the planet's atmosphere and surface. This wouldn't be a quick impact, it would be a prolonged, silent contamination. The radiation dose from the decay of these isotopes would poison the environment for years, leading to widespread radiation sickness, genetic damage, and the collapse of ecosystems. The very elements that signify wealth and beauty on our world would, in their raw, freshly forged state, be the agents of a slow and inescapable apocalypse, a final, ironic gift from a universe that creates and destroys in the same magnificent, violent act. While quasars represent the most brilliant and obvious manifestation of a feeding supermassive black hole, they are merely one member of a broader, more diverse family of cosmic powerhouses. At number 18, we expand our view to the overarching category of active galactic nuclei, or AN. This term encompasses any galaxy whose core is significantly brighter than can be explained by its stars alone, a clear sign that its central supermassive black hole is actively accreting matter and releasing a staggering amount of energy in the process. This family includes the hyperluminous quasars, but also their quieter but equally fascinating cousins, Seyfert galaxies and radio galaxies. Seyfert galaxies are like the nearby, less extreme versions of quasars. Our own Milky Way's neighbor, the beautiful spiral Messier 77, is a classic example. In a Seyfert, the brilliant core is still visible, but it doesn't completely outshine the host galaxy itself. We can still make out the spiral arms and structure, but the nucleus gleams with the light of a miniature quasar, powered by a black hole that is actively feasting. Radio galaxies, on the other hand, present a different spectacle. They may not always have the incredibly bright optical core, but they make up for it with their colossal twin jets. These are the AGN that launch the most powerful and extensive relativistic jets, which plow into the intergalactic medium, creating gigantic lobes that glow brightly at radio wavelengths, often stretching far beyond the visible confines of the galaxy itself. What makes all active galactic nuclei so dangerous beyond their raw power is their profound influence on their own homes. An AGN is not just a spectacle, it is the ultimate regulator of galactic evolution, and its primary mode of operation is sterilization. This process is known as AGN feedback, and it is a key reason why giant elliptical galaxies are often devoid of the gas needed to form new stars. The mechanism is terrifyingly effective. As the black hole feeds, the incredible radiation pouring from the accretion disk and the powerful winds it generates exert an immense outward pressure on the surrounding galactic gas. This isn't a gentle breeze, it's a hurricane of energy that physically blows the star-forming fuel right out of the galaxy. Imagine a vast reservoir of cold, dense hydrogen gas, the very raw material from which new stars are born. The radiation from the AGN heats this gas, preventing it from cooling and collapsing into stellar nurseries. Even more directly, the intense winds can sweep the gas away entirely, ejecting it into the galactic halo or beyond. In radio galaxies, the jets play a similar destructive role. As they plow through the galaxy's gas reservoirs, they shock and heat the material, effectively shutting down any ongoing star formation. The galaxy is left with an aging population of stars with no new generations to replace them. Over millions of years, the AGN methodically quenches its own galaxy, transforming a vibrant, star-forming spiral into a quiet, red and dead elliptical. It is a cosmic paradox where the engine at the very heart of a galaxy, powered by its greatest gravitational predator, ultimately ensures the long-term death of its creative potential, sterilizing its home from the inside out. But our journey now takes us from the observed and cataclysmic to the profoundly theoretical, to a danger woven into the very fabric of reality at the moment of its birth. At number 19, we confront a hypothetical relic of creation so strange it defies all conventional physics: cosmic strings. These are not strings in any sense we would recognize. They are not made of atoms or energy. Instead, imagine a one-dimensional crack in the universe itself, a flaw in the cooling of space-time left over from an infinitesimal fraction of a second after the Big Bang. According to some theories, as the super-hot, unified forces of the newborn cosmos began to differentiate and settle into the four we know today, the transition may not have been perfectly smooth. In some regions, the fields may have gotten stuck in a higher energy state, and where these different regions met, an unimaginably dense line-like defect could have formed, a cosmic string. A true cosmic string would be a line of pure mass energy, a thread finer than a proton but with the density of a galaxy. A single inch of this string could weigh millions of tons. It would be under immense tension, and this tension would cause it to vibrate and whip through the universe at nearly the speed of light. Unlike a black hole, it would not be hidden by an event horizon. Its presence would be betrayed only by its unimaginable gravitational influence on everything around it. Because it is a linear defect, its gravity would not be spherical like a planet or star. Instead, it would be what physicists call a gravitational deficit angle. Space around a cosmic string would be sharply folded, creating a unique form of gravitational lensing where an observer could see two identical images of a single galaxy, one on each side of the string with no distortion in between, a perfect cosmic double vision. The most immediate danger of a cosmic string is its sheer density. Should one pass through our solar system, its gravitational pull would be catastrophic. It would not gently tug on the planets, it would violently disrupt every single orbit simultaneously. The delicate clockwork that has held our system stable for billions of years would be instantly and irrevocably shattered. But this gravitational chaos pales in comparison to a far more direct and terrifying interaction. Because the string is a true one-dimensional object, it can slice through matter as if it weren't there. The concept is horrifyingly simple. If a cosmic string were to pass directly through the Earth, it would cut our planet in two as effortlessly as a wire slicing through cheese. There would be no explosion, no immense release of energy in the traditional sense. The cut would be so clean, so precise, and happen so quickly that the two halves of the planet would simply begin to drift apart, held together only by their own mutual gravity. For a brief, surreal moment, a chasm of empty space would exist running through the entire diameter of the Earth before the unimaginable pressure of the planetary interior caused it to catastrophically collapse inward. The result would be a global tectonic event of such magnitude that the planet's surface would be completely remade in a matter of hours, liquefied by the release of gravitational energy. The very concept of a hemisphere would become meaningless as the entire world convulsed into a molten ball of death. Perhaps the most bizarre and theoretical property of a cosmic string involves its effect on time. The extreme warping of spacetime around one could create closed time-like curves, a concept that allows for the possibility of time travel into the past. While the practicalities and paradoxes of this are purely in the realm of theoretical physics, it adds another layer of profound strangeness to these objects. They are not merely destroyers of worlds, they are potential unravelers of causality itself, capable of twisting the timeline of the universe into a knot. While no definitive evidence for cosmic strings has ever been found, their potential existence remains one of the most captivating and terrifying ideas in all of cosmology, a reminder that the early universe may have left behind traps of unimaginable power, silent wires of cosmic mass waiting for a chance to snap through reality itself. Yet for all the immense power of black holes and the explosive fury of supernova, there exists a hypothetical danger that makes them all seem trivial, a threat not just to planets or stars, but to the fundamental rules of existence itself. This brings us to the number 20 spot on our countdown, and to one of the most unsettling concepts in all of theoretical physics: vacuum decay. Imagine a single, tiny bubble spontaneously forming somewhere in the universe, perhaps triggered by a random quantum fluctuation or a high-energy particle collision. This bubble would not be made of air or energy, but of a new state of reality, a region where the underlying quantum fields that govern physics have suddenly fallen into a lower, more stable energy state. This is the true vacuum, and its emergence would be the ultimate cosmic catastrophe. To understand why, we need to delve into a strange property of our universe. The Higgs field, which gives particles their mass, exists in what physicists call a false vacuum state. Think of it like a ball resting in a small divot on the side of a much larger, steeper hill. It seems stable for now, but there is a far deeper valley below it, a state of lower energy. Our entire reality, the laws of physics as we know them, the forces that hold atoms together, are all dependent on the Higgs field being perched in that precarious higher energy divot. If something were to ever knock that ball out of its rut, sending it tumbling down into the true vacuum valley, the results would be both instantaneous and absolute. The moment this true vacuum bubble forms, a new set of physical laws would take hold within it. The fundamental constants that make our universe possible, the strength of gravity, the nuclear forces, the very existence of atoms, could be completely altered. But the true horror is that this bubble would not remain a localized anomaly. The boundary between this new reality and our old one would be under immense tension, causing the bubble to expand in all directions at the speed of light. Nothing can outrun this wall of absolute change, As it expands, it would not destroy matter in a fiery explosion. It would simply rewrite the software of the universe. Every atom, every star, every galaxy it enveloped would cease to function under the old rules. Protons might instantly decay, atomic nuclei would disintegrate, and the very fabric of matter would unravel into a new, unknowable form. The universe as we know it would simply be erased, replaced by a different reality that may not be able to support any complex structures, let alone life. The most terrifying aspects of vacuum decay are its stealth and its inevitability. There would be no warning. The bubble could form anywhere at any time, and because its expansion is luminal, we would have no way to see it coming. The first sign of its arrival would be the end itself, a wall of light that is not light, but the leading edge of a new physics that instantly and permanently cancels our existence. It is the ultimate reset button, a threat that is not just undetectable and inescapable, but one that operates on a level so fundamental that it questions the very permanence of the reality we take for granted. But what if the most dangerous black holes weren't the colossal monsters at the centers of galaxies, but the smallest, most ancient, and stealthiest of them all? At number 21, we consider a threat born not from dying stars, but from the very birth pangs of the universe itself, primordial black holes. These are not the stellar mass or supermassive black holes we've encountered so far. They are hypothetical relics forged in the unimaginable density and pressure of the first fraction of a second after the Big Bang. In that seething cauldron of nascent reality, random fluctuations in density could have been so extreme that pockets of matter collapsed directly into black holes, bypassing the need for a star's death altogether. The scale of these objects is what makes them so bizarre and so menacing. Unlike their stellar cousins, primordial black holes wouldn't conform to a standard size. They could be almost any mass, from a speck smaller than an atom to a lump as massive as a large asteroid. Their size is directly tied to their mass, and this leads to a truly strange property. A black hole with the mass of a small mountain would be no larger than a single proton. Imagine an object with the gravitational pull of an entire asteroid, yet compressed into a space 1,000,000 times smaller than a grain of sand. This microscopic point of infinite density would be virtually impossible to detect with our current technology, a ghost of gravity moving silently through the cosmos. This incredible stealth is the source of their profound danger. A primordial black hole with the mass of 1,000,000,000 tons could be zipping through our solar system right now, and we would have no idea it was there. It wouldn't emit significant Hawking radiation, it wouldn't have an accretion disk to glow, and it would be far too small to noticeably perturb the orbits of planets with its gravity until it was already extremely close. It could be sailing through the emptiness between worlds, a cosmic bullet waiting to strike. The nature of the impact, however, wouldn't be like a traditional asteroid collision. There would be no fiery explosion in the atmosphere. Instead, the infinitesimally small black hole would simply pass through the Earth as if it weren't even there. Because it's so tiny, the chances of it actually hitting a nucleus of an atom in our planet are incredibly small. It would slice through the crust, the mantle, and the core, exiting out the other side in a matter of minutes, leaving behind a microscopic tunnel of slightly disrupted atoms. On the surface, the event might be detected only as a faint, simultaneous tremor of identical strength at 2 points on opposite sides of the globe, a seismic whisper of something unimaginably strange passing through. But the real terror lies in the energy release along its path. Even though it's tiny, its gravitational field is immense for its size. As it travels through the dense interior of our planet, it would gravitationally attract the matter around it, pulling atoms toward its path. These atoms would then collide with each other at tremendous speeds behind the black hole, creating a wake of superheated plasma. This process, known as accretion, would deposit a significant amount of energy into the Earth's interior. A larger primordial black hole, perhaps with the mass of the asteroid series, would be catastrophic. Its passage would pump enough heat into the mantle to trigger massive volcanic upheavals, potentially waking supervolcanoes and causing global tectonic chaos. It would be the ultimate internal threat, a deep Earth trauma delivered by a particle-sized object, leaving a legacy of fire and eruptions in its wake without ever making a visible mark on the sky. The idea that our planet could be sterilized from within by a relic from the dawn of time, an object we could never hope to see coming, is a chilling capstone to the dangers lurking in the darkness. While we often worry about asteroids from our own solar system, history's most devastating impacts may actually come from beyond our sun's influence, launched from the darkness between the stars. Taking the number 22 spot are interstellar asteroids and comets, silent wanderers that traverse the immense voids between star systems, carrying with them the potential for impacts of unparalleled force. These are not local rocks nudged into new orbits. These are true extrasolar visitors, accelerated to incredible speeds by the gravitational dynamics of their home systems or galactic tides, making them the fastest natural projectiles in the galaxy. The existence of these objects moved from theory to stunning reality in 2017 with the discovery of Oumuamua, the first known interstellar object to pass through our solar system. Its name, Hawaiian for scout or messenger from afar, was eerily appropriate. This strange, elongated body was traveling at a blistering 87,000 miles per hour relative to the Sun, on a hyperbolic orbit that proved it was not bound by our star's gravity. It was just passing through. Then, in 2019, we spotted a second visitor, Comet Borisov, a more familiar icy body also on an unmistakable escape trajectory from our solar system. These two discoveries confirmed a long-held suspicion. The space between stars is not empty. It is filled with a vast population of icy and rocky debris, the leftovers from planet formation around other stars, ejected by gravitational interactions and set adrift on infinite journeys. The danger of an interstellar object is defined by its incredible kinetic energy. The force of an impact is determined by both the object's mass and the square of its velocity. An interstellar comet or asteroid doesn't just have a little more speed than a local one. It can be moving many times faster. A typical asteroid from our main belt might impact Earth at around 40,000 miles per hour. An interstellar object, however, could easily be traveling at over 150,000 miles per hour. This difference in velocity isn't just additive, it's multiplicative for the energy released. An interstellar object just half a mile wide could strike with the energy of a local asteroid 10 miles across, delivering an impact measured not in megatons, but in teratons of TNT equivalent. This immense speed also translates into an almost complete lack of warning. Our planetary defense systems are designed to scan the skies for objects orbiting our sun, whose paths we can calculate years or even decades in advance. An interstellar object, by contrast, would come from a random direction, far from the ecliptic plane where we expect to find most solar system objects. It would be traveling so fast that we might only detect it a few days or weeks before impact, far too late to mount any meaningful deflection mission. It would appear as a faint, fast-moving speck, quickly brightening from a new point of light into a world-ending fireball with terrifying swiftness. The aftermath of such a strike is almost too horrific to contemplate. The initial impact would vaporize a continent-sized portion of the planet's crust, ejecting trillions of tons of superheated rock and debris into the atmosphere. The global firestorm ignited by the re-entering ejector would circle the globe, scorching the surface, but the real, long-term extinction mechanism would be the impact winter that followed. The dust and sulfur aerosols would blot out the sun for years, collapsing the photosynthetic base of the food chain and plunging the planet into a deep freeze. The event would likely surpass the severity of the Chicxulub impact that wiped out the dinosaurs, simply due to the raw, unprecedented energy delivered in an instant by a visitor from the stars. It is a sobering reminder that existential threats to our world are not confined to our own solar system. They can and do come from the great dark between the stars, silent and swift, offering no warning and no second chance. But our journey into cosmic perils now leads us to a dance of ultimate darkness, a gravitational tango between two of the universe's most perfect predators. At number 23, we find stellar mass black hole binaries, systems where not one, but two black holes are locked in a mutual orbit, destined for a collision that will literally shake the foundations of the cosmos. These are not the quiet, solitary wanderers we encountered earlier. They are gravitational wave factories, and their existence creates a zone of chaos where the very laws of orbital motion become instruments of annihilation. The formation of such a system is a story of stellar life and death on a grand scale. It begins with a binary star system where both stars are true cosmic titans, each many times more massive than our Sun. These stars live fast and die young, both exploding as supernova within a relatively short cosmic time frame. If the supernova explosions are not perfectly symmetrical, and they almost never are, the resulting kicks can send the newborn black holes careening through space. But if the stars were initially bound in a tight enough orbit and the kicks aren't too violent, the two black holes can remain gravitationally shackled to each other. They become a binary pair, two invisible spheres of pure gravity circling one another in the void, their presence betrayed only by their influence on any nearby matter, or eventually by the ripples they send through space-time itself. For billions of years, this dance continues, a slow and stately waltz governed by Einstein's theory of relativity. But unlike planetary orbits, which are stable for eons, the orbit of a black hole binary is perpetually decaying. With every loop, the immense masses moving at a significant fraction of the speed of light radiate energy away in the form of gravitational waves. These ripples in the fabric of space-time carry away orbital energy, causing the two black holes to spiral inexorably closer. Their dance accelerates, becoming a frantic, ever-quickening whirl in the final moments before merger. The frequency of their orbit rises into the audible range for our detectors, creating the famous chirp signal that LIGO and Virgo have now heard dozens of times. Yet the true, insidious danger of such a system is not the final merger, but the chaotic gravitational environment in the millennia leading up to it. Any planet that somehow managed to form in this system or was captured by it would be living in a gravitational nightmare. The stable, elliptical orbits we take for granted in our solar system simply cannot exist here. The powerful and constantly shifting gravitational fields from two massive points would create a dynamic and violently unstable three-body problem. A planet's path would be utterly unpredictable, subject to extreme gravitational perturbations with every orbit. The most likely fate for such a world would be ejection. The complex interplay of gravitational forces could easily slingshot the planet out of the system entirely at a significant fraction of the speed of light, condemning it to an eternal, sunless journey through the interstellar void as a rogue planet. Alternatively, its orbit could decay, sending it on a death spiral inward toward the binary pair. As it ventured too close, the differential gravity between the near and far side of the planet, the tidal force, would become overwhelming. The world would be stretched and squeezed, its crust fracturing and its mantle boiling in a planetary-scale earthquake before it was finally shredded into a stream of debris that would spiral into the black hole's accretion disks. This would be a spectacular but fleeting feast for the black holes, a brief flash of light in the X-ray spectrum as the planet's material was vaporized, marking the end of a world that never stood a gravitational chance. The merger itself is the grand finale, an event of such raw power that it defies easy description. In the last seconds, the two black holes, now separated by only a few hundred miles, whip around each other hundreds of times per second. They distort each other's event horizons, stretching and merging into a single, peanut-shaped object of pure spacetime curvature before finally coalescing into a new, larger black hole. The energy released in this final moment is staggering. A significant portion of their combined mass is converted directly into energy in the form of gravitational waves, as dictated by E equals mc squared. For a brief instant, the power radiated in these waves exceeds the combined light output of every star in the observable universe. The newborn black hole then rings like a bell, its surface vibrating and settling down into a perfect sphere, sending out a final fading whisper of gravitational waves to announce its birth to the cosmos. It is the universe's most powerful symphony, played on instruments of pure gravity, a cataclysm that reshapes the fabric of reality itself while erasing any trace of the worlds that once may have foolishly called it home. Yet even the immense power of colliding black holes operates on a scale we can, in theory, comprehend. There exists a gravitational mystery so vast that it dictates the motion of our entire galaxy and everything around it, pulling us toward an unseen destiny in the cosmic dark. This brings us to number 24 on our countdown, a gravitational anomaly of such colossal proportions that it has puzzled astronomers for decades, the Great Attractor. Imagine a force so powerful it can tug on entire galaxies, including our own Milky Way, guiding them on a relentless journey we are only just beginning to understand. This isn't a single object, but a focal point of immense gravity, a cosmic whirlpool drawing in everything in our intergalactic neighborhood. Our story begins not with a visible landmark, but with motion. For years, astronomers have meticulously mapped the velocities of galaxies within our local cosmic vicinity, a region spanning hundreds of millions of light-years known as the Laniakea supercluster. They noticed something profoundly strange. Every galaxy, including ours, is not moving randomly. Instead, we are all streaming toward a specific point in the sky, located in the direction of the southern constellations Centaurus and Norma, at a velocity of over 14 million miles per hour. This shared, fatalistic motion implies a gravitational source of almost unimaginable mass, a gravitational anchor point dubbed the Great Attractor. The core of the mystery and the danger lies in its invisibility. For a long time, this region of the sky was almost impossible to observe directly because it lies directly behind the plane of our own Milky Way galaxy. This zone is obscured by thick clouds of interstellar gas and dust, a celestial blind spot that hid the attractor's true nature from our optical telescopes. It was a classic cosmic detective story. We could see the effect, the relentless pull, but we couldn't see the cause. Initial theories proposed it was a massive concentration of mass, perhaps a huge cluster of galaxies or a supercluster itself, exerting its gravitational influence. The unsettling implication was that something with the mass of tens of thousands of Milky Way galaxies was lurking in the shadows, dictating our cosmic fate. As observation technology advanced, particularly in X-ray and radio wavelengths that can pierce through the galactic dust, the picture began to clarify, yet the scale of the phenomenon only grew more immense. We now know the original Great Attractor is part of a much larger structure. The primary gravitational source is the Norma cluster, a massive conglomerate of galaxies, but its pull is merely the first step in a much grander gravitational hierarchy. Behind it lies an even more massive concentration of mass, the Shapley supercluster, one of the largest known structures in the observable universe, containing dozens of massive galaxy clusters. This distant titan is amplifying the pull, acting as the ultimate destination in our galaxy's long-term trajectory. So, if the Great Attractor is just a confluence of massive superclusters, where does the danger lie? The threat is not one of collision or instant annihilation, but of a grand, inescapable cosmic fate. The danger is one of isolation and the eventual heat death of a far-flung future. As our local group of galaxies continues this multi-million-year journey deeper into the gravitational well of these superclusters, we are being drawn away from the vast, empty voids that make up most of the universe. We are being herded into a denser and denser region of the cosmic web. In the extremely long term, this has profound implications. As galaxies in these dense regions interact and merge, the frantic pace of star formation will eventually cease, leaving behind mostly dead red stars and giant elliptical galaxies. The very fate of our entire local universe is being shaped by this relentless pull. For scientists, the continuing mystery also holds a more profound danger: the possibility that our understanding of gravity itself is incomplete. While dark matter is the leading explanation for the immense mass required for such a pull, the Great Attractor remains a prime candidate for phenomena that could challenge our fundamental models of physics. It is a constant reminder that the largest forces governing the cosmos are still hidden from view, pulling the strings of destiny from behind a veil of dust and stars, guiding not just our galaxy, but the future of everything around us toward an unknown, crowded, and final destination. And so we reach the end of our harrowing tour, a journey that has taken us from the silent, invisible predators like rogue black holes to the universe's most violent, brilliant blazes like hypernova and quasars. We've stood in the shadow of magnetars capable of sterilizing galaxies from across the cosmos and contemplated the silent, creeping doom of a dark matter clump passing through our world. This is the universe unmasked, not a serene, static painting, but a dynamic, often violent arena where creation and destruction are forever entwined in a dance of unimaginable power. These 25 objects are not mere curiosities. They are a testament to the extreme forces that shape existence itself, reminding us that the cosmos operates on a scale of energy and time that can humble any soul. In the face of such grandeur and terror, our place can feel terrifyingly fragile. We exist on a tiny, rocky world orbiting an average star in the quiet suburbs of a spiral galaxy, protected by a thin veil of atmosphere. Everything we have ever known, every triumph and tragedy of human history, has occurred on this pale blue dot. And yet, as we've seen, that dot, and the intricate web of life it supports, is vulnerable to forces from which there is no warning and no defense. A single flicker of a gamma-ray burst, a chance encounter with a rogue planet, or a distant black hole's jet momentarily aligning with Earth could rewrite our story in an instant. This is not a reason for despair, but for a profound and clear-eyed perspective. Our fragility is not a weakness. It is the very condition that makes our existence so precious, so statistically improbable, and so worthy of cherishing and protecting. This realization is the source of true awe. The same violent processes that threaten us are also the very reason we are here. The iron in our blood was forged in the heart of a Type I supernova. The gold in a wedding ring was minted in the collision of two neutron stars. The oxygen we breathe, the carbon that forms our bodies, all were cooked in the nuclear furnaces of long-dead stars and scattered across the galaxy by their explosive deaths. We are not just inhabitants of the universe, we are literally made from it, a collection of stardust that has temporarily coalesced into a form that can ponder its own origins. The terrifying dangers we've explored are not separate from us, they are our creators. This is the ultimate cosmic paradox. We are children of chaos, living in a precarious balance made possible by the very violence that could one day end it. So what do we do with this knowledge? We do not hide from it, we lean into it. We channel that humbling awareness into a driving curiosity. Look up at the night sky again, but see it now with new eyes. See it not just for its beauty, but for its story, a story of titanic forces, of ancient light from explosions that occurred millions of years ago, of invisible gravitational fields guiding the motion of galaxies. Let that sense of wonder fuel a desire to understand more. Follow the work of astronomers and physicists who are using incredible tools to map these dangers and unravel the mysteries of the cosmos. Their work is our window into this grand, terrifying, and beautiful reality. Let this new perspective also inspire a greater commitment to our own world. Understanding the cosmic threats beyond our control should sharpen our focus on the planetary challenges we can address. It deepens the imperative to safeguard our fragile biosphere, to cherish our unique and beautiful planet, and to strive for a future where humanity can continue to look up at the stars, not with fear, but with an ever-growing sense of wonder and a relentless thirst for discovery. The universe is vast, ancient, and filled with wonders and dangers beyond our comprehension. Our time here is brief, so go outside tonight, find a dark spot, and simply look up. See the cosmos for what it truly is, and feel that thrilling mixture of terror and awe. The adventure of understanding has only just begun.